Have you ever looked up at the night sky and wondered about the biggest mysteries of the universe? We see stars, planets, and galaxies, but what about the things we can't see? I'm talking about black holes, those cosmic monsters so dense that not even light can escape. For a long time, we thought they were the universe's ultimate prisons, where anything that falls in is lost forever. But what if I told you that even black holes can't last forever? What if they slowly leak, shrink, and eventually disappear? This isn't science fiction. This is the mind-bending reality of a phenomenon called Hawking radiation. Today, we're going on a journey to the edge of a black hole to understand one of the most brilliant ideas in modern physics, a concept that bridges the gap between the world of the very big gravity and space-time and the world of the very small quantum mechanics. This idea, proposed by the legendary physicist Stephen Hawking in 1974, completely changed our understanding of black holes. So, grab your thinking caps, because we're about to dive deep into the quantum weirdness that allows black holes to glow. First, let's get a quick refresher on what a black hole is. Imagine a star much more massive than our sun. When it runs out of fuel, it collapses under its own immense gravity. This collapse is so extreme that it squeezes all that mass into an infinitesimally small point called a singularity. Surrounding this singularity is an invisible boundary called the event horizon. Think of it as the point of no return. Once you cross it, the gravitational pull is so strong that you can't escape, no matter how fast you travel. That's why they're called black holes. Light itself gets trapped, so they don't emit any light of their own. For decades, this was the accepted picture. A black hole was a one-way street. It could only grow, gobbling up gas, dust, stars, and anything else that strayed too close. It was a perfect cosmic roach motel. Things check in, but they don't check out. But Stephen Hawking came along and asked a simple yet profound question. What happens when you apply the strange rules of quantum mechanics to the area just outside a black hole S-event horizon? This is where things get truly bizarre. According to quantum field theory, empty space isn't really empty. It's a bubbling, frothing sea of energy, a chaotic dance of what we call virtual particles. These particles pop into existence in pairs, seemingly out of nothing. There's a particle and its corresponding antiparticle, for example, an electron and a positron. They exist for an infinitesimally small fraction of a second, borrowing a tiny amount of energy from the vacuum, before they find each other again and annihilate, paying back their energy debt. This happens everywhere in the universe, all the time. It's the background hum of reality. Normally, this process is completely unnoticeable. The particle pairs are created and destroyed so quickly that they don't have any lasting effect. But what happens if this process occurs right on the razor S edge of a black hole S-event horizon? This is the key to Hawking's genius insight. Imagine a pair of virtual particles, let's call them particle A and particle B, popping into existence right at the event horizon. Due to the extreme gravitational forces, several things could happen. Most of the time, they'll just annihilate each other as usual. But every now and then, something incredible occurs. Particle A might fall into the black hole, crossing the event horizon, while particle B manages to escape, flying off into space. From the perspective of a distant observer, it looks like the black hole has just spat out a particle. This escaping particle, particle B, is no longer virtual. It has become a real particle, carrying real energy away from the black hole. But wait, where did this energy come from? We know that energy can't be created from nothing. This is one of the fundamental laws of physics, the conservation of energy. This is the most crucial part of the theory. Remember its partner, particle A? The one that fell into the black hole? Quantum mechanics has a neat trick for this. The virtual particle that falls into the black hole is considered to have negative energy. When this negative energy particle enters the black hole, It reduces the black hole's total mass and energy. Think of it like this. If a black hole has a mass of x, and it absorbs something with an energy of negative y, its new mass is x minus y. It actually gets lighter. So, the black hole pays the energy bill for the particle that escaped. By sacrificing a tiny bit of its own mass, it allows the escaping particle to become real. To an outside observer, it appears as if the black hole is emitting a faint glow of particles. This glow is what we call Hawking radiation. Now, this process is incredibly slow. For a black hole the mass of our Sun, the temperature of this radiation would be just a tiny fraction of a degree above absolute zero. You'd need an impossibly sensitive thermometer to even detect it. The rate of evaporation is so slow that it would take a solar mass black hole about 10 to the power of 67 years to evaporate completely. To put that into perspective, the current age of the universe is a mere 13.8 billion years, or about 10 to the power of 10. So we're talking about a timescale that is almost unimaginably long. However, the story is different for smaller black holes. The smaller a black hole is, the hotter it is, and the faster it radiates its mass away. A black hole with the mass of a large mountain, for instance, would be radiating at a temperature of billions of degrees, and would evaporate in a bright flash of energy in less than a second. Some theories suggest that tiny, primordial black holes might have been formed in the chaos of the Big Bang. If so, those with the right starting mass would be reaching the end of their lives right now, disappearing in a final powerful burst of gamma rays. Astronomers are actively searching for these flashes, as detecting one would be direct evidence of Hawking radiation. The implications of this are staggering. Hawking radiation tells us that black holes are not eternal. They have a finite lifespan. They are not just cosmic drains, but dynamic objects that interact with the universe in a subtle, quantum way. They aren't truly black after all. They have a temperature and they glow, albeit very, very faintly. This theory also gave rise to one of the biggest puzzles in modern physics, the black hole information paradox. One of the core principles of quantum mechanics is that information can never be truly destroyed. It can be scrambled, hidden, or rearranged, but the fundamental information about a particle's state is always preserved. But what happens when something, say a book, falls into a black hole? The information contained in that book, the arrangement of atoms, the words on the page, seems to be lost forever behind the event horizon. Then the black hole slowly evaporates via Hawking radiation. The radiation that comes out is predicted to be random thermal. It contains no information about what fell in. It only depends on the black hole's mass, charge, and spin. So, when the black hole is completely gone, where did the information from the book go? Is it destroyed? If it is destroyed, it violates a fundamental law of quantum mechanics. If it's not, how does it get out? This paradox has been a battleground for theoretical physicists for decades, leading to wild and fascinating ideas like the holographic principle, which suggests that all the information that falls into a black hole is somehow encoded on its two-dimensional event horizon. It is a puzzle that pushes the limits of our understanding and hints that we still missing a key piece of the theory of everything. Hawking radiation is more than just a theory about black holes. It's a beautiful synthesis of Albert Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the bizarre world of particles and forces. These two theories are the twin pillars of modern physics, but they notoriously don't play well together. Hawking radiation is one of the first and most successful attempts to unite them, giving us a tantalizing glimpse into a deeper theory of quantum gravity. So, while we have yet to directly observe Hawking radiation, it's far too faint for our current technology. Its theoretical foundation is solid, and it has profound consequences for our understanding of the cosmos. It transformed black holes from simple, static objects into complex, dynamic systems that participate in the life cycle of the universe. It shows that even in the most extreme places, the weird and wonderful rules of quantum mechanics are at play, slowly but surely reshaping the fabric of space-time. The next time you look at the stars, remember the hidden drama unfolding in the darkest corners of the universe. Remember the black holes, not as eternal prisons, but as cosmic furnaces, slowly radiating their energy back into the void, governed by the elegant and mysterious laws discovered by one of our generation's greatest minds. They are a testament to the fact that in science, asking the right question can illuminate the entire universe. Thanks so much for joining me on this deep dive into one of physics' most mind-bending topics. If you enjoyed this journey to the edge of reality, please hit that like button and subscribe for more explorations into the mysteries of our universe. And let me know in the comments, what cosmic mystery do you want to explore next? See you in the next video. Have you ever looked up at the night sky and wondered about the ultimate fate of the universe? We often think of black holes as cosmic monsters, devouring everything that gets too close, destined to exist forever. But what if I told you that even these giants have an expiration date? What if black holes aren't entirely black after all? This is the story of Hawking radiation, one of the most mind-bending ideas in modern physics, a concept that completely changed our understanding of black holes. It has a tale that brings together the two great pillars of physics: Einstein's theory of general relativity, which describes the universe on a grand scale, and quantum mechanics, the strange and wonderful rules that govern the microscopic world. To understand how a black hole can radiate anything, we first need to visit the bizarre world of quantum mechanics. According to quantum field theory, what we perceive as empty space is anything but empty. It's a seething, bubbling cauldron of activity. Virtual particles are constantly popping into existence in pairs, a particle and its antiparticle. They exist for a fleeting moment, an impossibly short time, before they find each other again and annihilate, disappearing back into the vacuum. Think of it like borrowing a tiny amount of energy from the universe, just long enough to exist before paying it back. This happens everywhere, all the time, even right here in this room. Normally, this process has no observable effect. But things get interesting near the event horizon of a black hole. The event horizon is the point of no return. Once something crosses it, not even light can escape the black hole's immense gravitational pull. Now, imagine one of these virtual particle pairs popping into existence right on the edge of the event horizon. It's a cosmic game of chance. Usually, they'd annihilate each other instantly. But what if, in that split second, one particle falls into the black hole, while the other one manages to escape? The particle that falls in is lost forever. Its partner, now stranded outside the event horizon, can no longer annihilate with it. It becomes a real particle, free to fly off into space. To an outside observer, it looks like the black hole has just emitted a particle. This steady stream of escaping particles is what we call Hawking radiation. But there's a catch. Remember how these particles borrowed energy from the universe to exist. When one particle falls into the black hole and the other escapes, that energy debt has to be paid. And where does the energy come from? It comes from the black hole itself. The particle that falls in actually has negative energy relative to the universe outside. So, when the black hole swallows this negative energy particle, its total mass and energy decrease. It's a bit like paying a bill. Your bank account gets a little smaller. This is the genius of Stephen Hawking's discovery. He showed that because of this quantum effect, black holes aren't truly black. They glow, albeit incredibly faintly, and over immense timescales, they actually lose mass. They evaporate. This leads to a fascinating paradox. The size of the black hole matters a great deal. The rate of evaporation is inversely proportional to its mass. This means smaller black holes are hotter and evaporate much faster than larger ones. A truly massive black hole, Like the supermassive one at the center of our Milky Way galaxy, Sagittarius A** is colossal. It has a mass of about 4 million suns. For a black hole this size, the Hawking radiation is unbelievably weak. Its temperature is just a tiny fraction of a degree above absolute zero. It's actually absorbing more energy from the cosmic microwave background radiation, the leftover heat from the Big Bang, and it's losing through evaporation. So for now, it's still growing. But let's think about a stellar mass black hole, one with the mass of, say, our Sun. Even for this smaller black hole, the evaporation process is staggeringly slow. The time it would take for a solar mass black hole to completely evaporate is a 1 followed by 67 zeros. That's trillions upon trillions of times longer than the current age of the universe. We're talking about timescales that are almost impossible for the human mind to comprehend. However, the story changes if we consider hypothetical primordial black holes. These are theoretical black holes that might have formed in the chaotic, dense conditions of the very early universe, just moments after the Big Bang. Some of these could have been microscopic, perhaps with the mass of a mountain or even an asteroid. A primordial black hole with the mass of a large mountain would have a temperature hot enough to radiate X-rays and gamma rays. Its lifetime would be closer to the current age of the universe. If such a black hole existed, it would be in its final explosive moments right about now. As a black hole evaporates, it gets smaller and smaller. As it gets smaller, its temperature skyrockets, and it radiates energy away faster and faster. This creates a runaway process. In its final second of life, a tiny black hole would unleash a final, tremendous burst of energy, equivalent to millions of nuclear bombs going off all at once. Astronomers are actively searching for these gamma-ray bursts, as they would be the smoking gun for Hawking radiation and the existence of primordial black holes. So far, we haven't found any definitive evidence, but the search continues. The implications of Hawking radiation are profound. It beautifully connects 3 fundamental areas of physics: general relativity, the theory of gravity, and space-time; quantum mechanics, the theory of the very small; and thermodynamics, the science of heat and energy. A black hole, it turns out, has a temperature and an entropy, which is a measure of its disorder. This was a revolutionary idea. It suggests a deep underlying connection between these seemingly separate fields, a hint at a theory of everything that physicists have been searching for. But Hawking as discovery also created one of the biggest puzzles in modern physics: the black hole information paradox. One of the core principles of quantum mechanics is that information can never be truly lost. It can be scrambled, hidden, or rearranged, but it's always there in some form. So, what happens to the information about all the things that fall into a black hole? If you throw a book into a black hole, the information about its cover, its pages, and the words written on them gets absorbed. According to relativity, that information is trapped behind the event horizon, lost forever. But if the black hole eventually evaporates completely, turning into a featureless bath of thermal Hawking radiation, where did all that information go? The radiation itself seems random and contains no clues about what fell in. Did the information just vanish from the universe? This would violate the fundamental laws of quantum mechanics. This paradox has been a battleground for theoretical physicists for decades. Is our understanding of quantum mechanics wrong? Is our understanding of gravity wrong? Or is there some missing piece of the puzzle that reconciles the two? Scientists have proposed many exotic solutions, from the idea that information is somehow encoded on the surface of the event horizon like a hologram, to the possibility that tiny remnants are left behind after evaporation, or even that information escapes into other universes. There's no consensus yet, but the quest to solve this paradox is pushing the boundaries of what we know about reality itself. So, while we may never directly observe a black hole evaporating, the concept of Hawking radiation has completely reshaped our cosmic perspective. It tells us that even the most permanent-seeming objects in the universe are subject to change. It reveals a hidden dynamic life for black holes, where they glow, shrink, and eventually may disappear in a final flash of glory. It is a testament to the power of human curiosity and a beautiful reminder that the universe is far more strange, interconnected, and wonderful than we could ever have imagined. Even in the darkest corners of space, there is light. Thank you so much for joining me on this journey to the edge of a black hole. If you found this as fascinating as I do, please hit that like button and subscribe for more deep dives into the mysteries of the cosmos. Let me know in the comments what you think about the information paradox. See you next time.